In Chapter 8, we begin our first real foray into inferential statistics. And in this chapter, what we're going to do is we're going to create confidence intervals for population parameters. Up until this point, the only thing that we've really had at our disposal are point estimates. And point estimates are good, but it's hard to know exactly how good. So say, for example, you wanted to find average rent for apartments in your area, or maybe you wanted to find average salary of stats teachers in your state, or maybe you wanted to find the proportion of people who prefer Popeyes over Chick-fil-A. Okay? Well, you could collect samples, and you could get a sample mean for average rent or for average salary. You could get a sample proportion for people who prefer one over the other. But the problem is, with these point estimates, right, X bar would be the mean, and P or P hat is what I typically use. Your textbook, I think, uses P prime. It's like P with a little apostrophe. But the problem with X bar and P hat or P prime is that we don't know whether or not our sample was very good, right? Even if we do a good job of using a random sampling technique, and we do the best job we possibly can, we still don't know for sure that we got a good representative sample. We might have some unusual values in our sample that could skew our results. So if all we have is a point estimate, a single point, then, or I should say a single value like X bar, then we don't know how good that value is. Okay? So that's the major shortcoming of these point estimates, is even though they tell us meaningful information, we don't know how good they are at predicting the population mean or proportion. So to give us something that we can have a little more faith in, something that we can know, all right, within a certain percentage probability, we think that the correct answer is this. All right, that's what confidence intervals are for. So basically, it's like a point estimate, only instead of a single value, it's a range of values. And we use probability with our probability distributions and the central limit theorem to get a range of values that we can have confidence in. Okay, so typically the way we construct confidence intervals is we start with the point estimate, which again is either X bar or P hat. And then we take the margin of error, which is a thing we calculate, and we subtract it from the mean and we add it to the mean, and that gives us a range of values where we can say, all right, we are such and so percent confident that the true population mean is in this range, which is better than what we can do for point estimates because we don't have any associated confidence level, right? We do the best we can and hope for the best, but we don't have a probability that tells us, how confident we can be in our answer. Confidence intervals give us that. So we'll start in section 1 with confidence intervals for means, where we already know the population standard deviation sigma. And this is a little bit of an unlikely scenario. It's really just not very likely that we could know the population mean without knowing the population standard deviation, because if we know one, oh wait, I think I said that backwards. It's unlikely we could know the standard deviation without knowing the mean, because you have to have the mean in order to calculate the standard deviation. So I don't know. It's a little far-fetched, but there are a couple of good reasons to do it. Number one, the calculations are relatively easy. We do have the calculator functions that make this pretty nice. So it's worthwhile, even if it's not necessarily super likely to happen in real life. So when we know the sigma, when we know standard deviation for the population, we use the normal distribution z. Okay, this is a central limit theorem kind of case. So our point estimate is X bar, and our margin of error, we call it the EBM, the error bound for a population mean. Sometimes I just refer to it all as margin of error, but we have error bound for a mean in this section, and then later we're going to have error bound for a proportion. So they use different The textbook uses EBM for means and EBP for proportions, just to make sure we don't get confused. But in any case, all of those are examples of margins of error. So we need to know how to calculate the EBM, but I'll show you that in just a minute. To start with, let's just look at a simple example. Suppose we've collected data from a sample and we know the sample mean but not the population mean. So if we find that the sample mean is 7 and the error bound is 2.5, then we can construct a confidence interval this way. We basically just take 7 minus 2.5 and we get 5.0. And then we can do 7 plus 2.5 to get 9.5. And then we can write our confidence interval 3 different ways. And I have another slide later on that goes into more detail. But the first is just an interval notation, which hopefully you've seen somewhere, Honors Algebra 2 or Pre-Calc or someplace. But that's just saying that this is an interval from 5 to 9.5. Okay, the second way to write it would be to write it as an inequality, to say that mu, which remember mu is the population mean, is between 5.0 and 9.5. And then the last way is just to write x bar, which is 7, plus or minus that error bound. Of the three, I think my preferred way to do it is the middle one with mu in it, because that helps to remind us what it is we're estimating. Okay, we are estimating the population mean, mu. And the other two methods don't refer to mu, and so I think sometimes it can get easy to lose sight of what we're actually doing. But if you use the middle way with the inequalities, then mu is right there in front of you. It helps you to remember what you're doing. All right, so the idea of a confidence interval depends on something called a confidence level. Okay, and this is typically determined before the outset of any calculations. Okay, perhaps in a certain environment, a certain level of confidence is required. Okay, like maybe you really need 99% confidence because you're in a medical field and you need to be really confident that your results are accurate, so you use a high confidence level. Or maybe it's a marketing thing and you want to have your marketing department working at a 90% confidence level. It doesn't need to be as exact as some other fields. So it'll depend on context and what your desired outcome is. But confidence level is kind of where it starts. We want to know what's the probability that we are correct, and that's going to be our confidence level. So, like I said, confidence level, the likelihood that our calculated interval is quote-unquote correct, meaning that the true population parameter is somewhere in our interval. So I'll let you read that. Technically, a little technical language, but we can think of it the way we originally said. So alpha is a second thing to note, and alpha will come back, and we'll look at alpha again in chapter 9. But alpha is the probability that we're wrong, basically. Okay, the probability that our interval does not contain the true population parameter. And the way you find alpha is 1 minus the confidence level. So another way of saying that is alpha plus the confidence level should add up to 1. All right, so just a visual here to try to help us understand what we're talking about in terms of the central limit theorem and the normal distribution. If, say, for example, we're working a problem and we want a 90% confidence level, all right, so that means that we are looking for the interval that would basically encompass the middle 90% of the normal bell curve. So see here, the purplish shaded region goes from 5 to 15. All right, so whatever scenario this graph is describing, we have a mean of 10, or I should say a sample mean of 10, and a margin of error of 5. And so 10 minus 5 gives us 5, 10 plus 5 gives us 15. And so between 5 and 15, we have 90% of that area between those two values, which means we have 10% in the white part that's not in the shaded area. And since the bell curve is symmetric, we know that must be 5.05 or 5% in each of those little tails. So this is a good visual, I think, to help you connect the central limit theorem that we did in chapter 7 to the confidence levels that we're dealing with now in chapter 8. So how do we calculate a confidence interval? Well, first thing we have to do is we have to find the sample mean. And, we did that ages ago. We found averages, means, quite a while ago, so I'm sure you know how to do that. And we don't have to calculate a standard deviation here because it has to be given to us. And we're basically assuming that the population standard deviation is already known, which means they have to tell us what it is. Now the z-score is, remember the formula for z-scores? We did that in chapter 6 for normal distribution, and we did it again a little bit with the central limit theorem in chapter 7, so hopefully you know how to do that. And then using those two things, we're going to calculate the error bound. So I'll walk through all of this here in just a minute, but then we're going to construct the confidence interval where we do x bar minus the error bound and x bar plus the error bound. Now, this one here is one that I really want to emphasize with you guys. You want to write a sentence that interprets the interval in the context of the problem. I actually am not worried about you guys being able to do this. I think you'll be just fine. But this is something, again, where it doesn't matter how good we are at doing the math problems if we can't convey our findings to somebody else. Okay, particularly when you're doing research, in the STEM Academy, your research capstone experience needs to use statistics appropriately and then convey those. So this is a really, really important part of what we're trying to accomplish. So find the z-score. Here's how we're going to do this. Using the tables is one way. The other way would be to use inverse normal in the calculator. But basically what we're doing is we're finding a z-score and we're giving it a kind of a special name. We're calling it z alpha over 2. And oftentimes this is just referred to as the critical value. Okay, so sometimes this z alpha over 2 is the critical value. I made it big over here on the right hand side just because I was afraid that the first one on the first line might be small or fuzzy or something on the video, but it's z with a subscript alpha over 2. Now, suppose we want to find a 95% confidence level. All right, so our alpha is 5% or 0.05. So our alpha over 2, okay, just dividing alpha by 2 would be 0.025. So that means that in each tail, right, if we go back for a moment and look at this, okay, that means in each of the tails where the white space is under the curve, each of those tails has 0.025 in it for this example. So that means that if I just consider the right-hand side tail, that means that the right-hand side tail has 0.025 and everything to the left of that would be 0.975. So that's what would go into inverse normal. So if you get your calculator out and you go second vars and you do inverse norm, INV norm, and put 0.975, you should get a z-score of 1.96, okay, or very close to it. Keep 1.96 in your mind, okay? Try to write that down somewhere prominent. It's a very, very common number because 95% confidence levels are probably the most common confidence level that we use, okay? So 1.96 is a real important number. We're going to work with some examples where we do different numbers, so you'll get to kind of get some experience, but 1.96 comes up a lot because 95% confidence levels come up a lot. So just be aware of that. Okay, here's our formula for the error bound of the mean. Our critical value, the z alpha over 2, times sigma, which again is given to us because we're assuming we already know it has to be given, divided by the square root of n. So notice, hopefully you remember, sigma divided by the square root of n, we called that last time, we called that the standard error of the mean. So we have the critical value times the standard error, and that gives us our margin of error, or our error bound. Okay. So in this example, suppose that we have scores on stats exams that are normally distributed with an unknown population mean and a standard deviation of 3 points. A random sample of 36 scores is taken and gives us a sample mean of 68. We want to find the error bound for a 90% confidence interval for the true population means of stats exam scores. Okay, notice first of all that that sample mean that's given, 68, that's not actually relevant to finding the error bound. We are going to use that later, but for now, we don't really need it. What we need is the critical value, that z alpha over 2. So remember that if we have a 90% confidence level, then we have an alpha of 10% or 0.1. And if we split that alpha into the two tails of the normal curve, that would give us 0.05 on each side. So the top tail has 0.05 in it, which means that everything else, the bottom part of the graph, the left part of the graph, would be 0.95. Okay, so running through that again, 90% confidence level means 10% alpha. Half of that is 5% or 0.05. So that means we're separating the top 5% and the bottom 95%. So we go to the calculator to do inverse normal, or you could use the z-score table if you prefer. But for now, I'm just going to assume you're going to use the inverse normal. So if you do that with 0.95, you get 1.645. So our critical value is 1.645. Now we plug that and the sigma, the standard deviation that we're given, which is 3, and the sample size, which is 36, and we should get an error of 0.8225. All right, so like I said before, there are 3 acceptable ways to write a confidence interval. The first is just in parentheses in interval notation. So you'll have your lower bound, the x bar minus the EBM, and then your upper bound, x bar plus the EBM. The second way, this is not in the same order that I did them before, but the second way would be just to write x bar plus or minus that error that you found. And then the third way would be to use the same numbers as in number 1, but include them in an inequality with mu, okay, where mu is greater than the lower bound and less than the upper bound. Taking that previous example and plugging in our numbers, we would have an x bar of 68 and an error bound of 0.8225. And so subtracting those two and then adding those two gives us 67.1775 and 68.8225. That's our first confidence interval. So we're saying that the mean is between those two numbers. The second way to do it would be to write x bar plus or minus our error. So that would be here, 68 plus or minus 0.8225. And the third way uses the same numbers as the first one, only we write it with an inequality with mu in the middle. So that tells us that mu is somewhere between 67.1775 and 68.8225. So how do we do these in the calculator? Well, you're going to go back to the Stat button. You're going to hit the right arrow until you get to the Tests menu. And then you go down to number 7, which is Z interval. Just keep in mind in Chapter 8, we're always doing intervals. So there are several other tests and things in there that look like the right one, but they end in test instead of int or interval. So make sure you're looking for intervals in the menu there. So there's 2 modes for getting solutions from Z-interval. One is the data mode, and in that case all you have to tell the calculator is sigma and what list to look for to get the data. Okay, you have to put the data into one of the lists, and then the confidence level. On the other hand, if instead of providing the list of data, perhaps you're just provided with some information such as what the sample mean was and how big the sample was, in which case you would select stats and then you put in sigma, the sample mean, the sample size, and the confidence level. To work this full example, we're going to construct a 98% confidence interval for radiation levels of cell phones. If you want more information on this, there's some in the textbook. I just basically pulled 1/3 of the table out of the book for us to do a quick example here. There are more numbers and some explanation in the textbook if you're interested. And we're told that the standard deviation is 0.337. We want to construct a 98% confidence interval. So the first thing that we need is to put our data into L1, and then once we have that, and in case you need some refresher, L1 is you hit stat and then edit, which is the very first option, so basically stat and then enter. And you put your data in L1. If you need to clear L1, you can highlight L1, hit clear, and then enter. It'll get rid of all that. So After we've got our data in L1, we go to Z interval. So that's stat, and then go over to the tests menu and go down to Z interval. We're going to select the data option because we have the raw data. And we need to tell the calculator sigma, 0.337. Need to tell it to look at L1, which if you need to know how to do that, if for some reason it says something other than L1, you hit second 1, and that will put L1 in there. And then frequency should be 1 already. If it's not, you need to change it to 1. And then the confidence level is 0.98. When you press enter on that, you should get a confidence interval of 0.86458 to 1.3604. To calculate the sample size that you need in order to get the results that you want, we need to use this formula. And when I say results that you want, typically what happens is we have a particular confidence level in mind, and then we might also have a particular margin of error in mind. So say we want to find the mean, let's say we want to find the mean salary for a particular profession, and we want to be accurate to within $1,000. Okay, so $1,000 would be our EBM, would be our error. Our confidence level, whatever that was, 95%, let's say, will tell us what Z alpha is. And then again, we're still assuming that we know the population standard deviation, so we'd have to put sigma in there. So typically this sample size calculation is used when we want a particular confidence level and a particular error, margin of error. And then we can plug them into this formula, and that'll tell us how large a sample we need. So just remember that we always need to round this number up. If we get a decimal, 302.1, we need to round that up to 303 so that we make sure that we have a large enough sample. It's okay to have a bigger than necessary sample. It's not okay to have one that's just slightly too small. Your homework for section 1 is 1 through 12. So please let me know if you have any questions about any of this, and I will talk to you later.